is a walkthrough of problem 3 on practice exam 1 in module 2, which is on page 49 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 3 is, a conducting sphere has a net charge of 0.4 nanocoulombs and a radius of 2 centimeters. It is surrounded by a conducting shell of radius 8 centimeters and thickness 1 millimeter that has a net charge Q. The electric field is 1,000 newtons per coulomb at a distance of 12 centimeters from the center of the sphere, and the field is radially outward. Part A, what is the net charge Q on the spherical shell? B, what is the net charge on the inner surface of the spherical shell? Part C, what is the net charge on the outer surface of the spherical shell? And part D, what is the electric field a distance of 4 centimeters from the center of the solid conducting sphere? Let's draw a good diagram. We're going to draw it in cross section. This is a sphere. That's a spherical shell that goes all the way around it. We have a slice right into the page. We know that the center sphere is 0.4 nanocoulombs. And we know that the field, 12 centimeters, which is outside of the shell, is 1,000 newtons per coulomb away, directly away, radially outward. 4 centimeter radius, 8 centimeter, 12 centimeters away. It's hard to keep in mind when you're looking at a situation in 2 dimensions that it's really a 3-dimensional problem. So the field lines are coming in every direction, sort of like this. That's a central sphere, not just in the plane of the paper, but in every direction. In the first 2 problems of the exam, here's the charge distribution. What's the field? Here we have the field. We want to know the charge on the spherical shell. Still Gauss's law. The only thing that's different is the unknown. So first we have to make a useful choice for a Gaussian surface. This is a sphere, that's a spherical shell. Our Gaussian surface should be a sphere. And since we know the field at this point, we should put the Gaussian surface through this point so we can plug in 1,000 newtons per coulomb for the electric field. There it is. Here's our Gaussian surface. And we know what E dot A is right here. There's the E, and the area is 4 pi r squared. And we know the radius is 12 centimeters. Surface area of a sphere, 4 pi r squared. Now we can solve for the charge enclosed. E, there's A, 4 pi k q enclosed. This time q enclosed is the unknown. We can solve for q enclosed, and we get 1.6 nanocoulombs. You have to be really careful here. 1.6 nanocoulombs is the charge enclosed by the Gaussian surface. It always is the charge enclosed by the Gaussian surface. There's 2 things here that have charge, this one and that one. And the total is 1.6 nanocoulombs. We want to know the charge on the spherical shell. A Gaussian surface includes both the shell and the solid sphere. We know the solid sphere has 0.4, so the shell must be 1.2. 1.2 nanocoulombs plus 0.4 nanocoulombs is 1.6 nanocoulombs. The charge on the spherical shell is plus 1.2 nanocoulombs. There it is. 1.2 nanocoulombs right here. Now, part B. What is the charge on the inner surface of the spherical shell? We know the total charge on the spherical shell is 1.2, but we don't know how much is on the inside, how much is on the outside. Is it 0.8, 0.8? Is it 0, 1.2? We have to figure it out. And we can figure it out by a really clever choice of a Gaussian surface. Let's put the Gaussian surface inside the metal, inside the spherical shell. Right in here, like this. There it is. There's the Gaussian surface. Our Gaussian surface encloses the inner surface of the shell, but it does not enclose the outer surface of the shell. The shell is conducting. It's given in the problem. It's a conducting shell. If there was a field there, the charges would move. Conductors are full of charges, full of electrons. Electrons are just sitting there. If there was a field there, they would respond to the field. There can't be a field inside of a conductor if no current is flowing. So we know the field is zero in there. So in our Gauss's law equation, E is zero. So the whole left-hand side drops out. E dot A is zero because E is zero. This means Q enclosed must be zero. There can't be any net charge inside of our Gaussian surface. And we know there's plus 0.4 on the shell. If there's plus 0.4 on the shell and the total enclosed is zero, there has to be minus 0.4 on the inner surface. The charge on the inner surface of the spherical shell is minus 0.4 nanocoulombs, got to be. Let's think about why that is. So this spherical shell has charges all around it. I just drew one representative charge. Positive charges have field lines going away from them. There can't be any field line going through the metal. Field line has to end on the inner surface of the metal. Field lines end on positive charges. In order for every charge that's making a field line in the sphere to end on a negative charge in the inner surface of the spherical shell, they have to be the same. Plus 4 nanocoulombs on the sphere, minus 0.4 nanocoulombs on the shell. All of the field lines are accounted for. No field lines penetrate through the metal. That's the answer to part B. Part C, what is the charge on the outer surface of the spherical shell? We know the inner surface has minus 0.4, and we know the total is plus 1.2. So the outer has to be plus 1.6. There we go. Plus 1.6 minus 0.4 plus 1.2. The charge on the outer surface of the spherical shell is plus 1.6 nanocoulomb. Part D asks for the field at 4 centimeters, which is outside the sphere but inside the shell. There's one representative field line. The field lines go all the way around, not just in the plane of the page, but directly at us, directly away from us. It's a sphere. So we make our Gaussian surface a sphere that goes through the point 4 centimeters from the center of the solid sphere. There it is. The radius of that spherical shell, 4 centimeters. Now we can use Gauss's law. E dot A is 4 pi k Q enclosed. Q enclosed is only the sphere, plus 0.4. And there's the radius, 0.04 meters. We can solve for E. And we get 2250. But we need the direction. This is positive. The field lines are going radially outward. The answer to part D, the electric field a distance 4 centimeters away from the center of the sphere is 2250 newtons per coulomb radially outward.